This is ytterbium. Here is ytterbium's atomic structure. So some facts about ytterbium. It is located in the lanthanides group in period 6 of the periodic table. Its atomic mass is 173.045 grams. It has a melting point of 824 degrees Celsius and a boiling point of 1196 degrees Celsius. It has 11 isotopes ranging from Ytterbium-166 to Ytterbium-177, with about 4 of those having known half-lives. So, the history of ytterbium. It was discovered by a man named Jean-Charles Galissard de Marignac in 1878, who also discovered a lot of the other elements. It was named after a Swedish town named Ytterby, where it was discovered, and it was found by being extracted from the element erbium. Some other facts about ytterbium. It is a soft silvery metal. It is beginning to find uses in memory devices such as this SD card and tunable lasers, which is the device in the top right corner, as well as industrial catalysts, which are chemicals used to speed up other chemical reactions. It has a low toxicity and there are no biological roles. It dissolves rapidly in strong mineral acids, and it slowly oxidizes in the air, making a protective outer layer. Here is a video about ytterbium explaining some of its history.
So ytterbium, it's a rare earth element, it's a metal, it's a silvery lustrous metal, it's very soft and it reacts very readily with oxygen to form a very nice protective oxide layer which sits over the metal, so it preserves itself after reaction with oxygen. It was first identified or first isolated from a sample of a mineral which was recovered from this very quarry where we are in Ytterby, near Stockholm in Sweden. But it took a very, very long time to make that extraction and to purify the metal. It's a rare earth element, it's one of 15, and it's actually the least abundant of the rare earths. But the name rare earth sort of makes you think that it's really rare. But if you look at its occurrence in the Earth's crust, it was a surprise to find that actually it's twice as abundant as tin. But that said, total production of ytterbium is only 50 tonnes per year. So it's still very, very little utilised. And that's probably because its chemistry is least understood. And it's least understood because we were only really able to isolate significant amounts of ytterbium in the late 1950s.
So this is Darmstadtium. Here is Darmstadtium's atomic structure. Some facts about Darmstadtium. It is located in group 10 of the transition metals in period 7. Its atomic mass is about 281 grams. Its boiling point, melting point, and density are all unknown. And it has 2 isotopes, Darmstadtium 281 with a half-life of 0.4 seconds, and Darmstadtium 279 with a half-life of 0.2 seconds. So its history, it was discovered in 1994 by 3 men, Sigurd Hoffman, which is the man in the top left, Peter Armbruster, which is the man in the middle, and Gottfried Münzenberg, which is the man at the right. It was named after the town Darmstadt, Germany, where it was discovered, and it was created by fusing lead with nickel in a heavy ion accelerator. Some other facts about Darmstadtium. It's radioactive, so there is no actual images of the element. Only a few atoms of Darmstadtium have ever been made, and it hasn't been used in anything except research in the lab. So here is a video that explains about Darmstadtium, and it also shows a heavy ion accelerator, which was used to make Darmstadtium.
Darmstadtium, like the other of these very heavy elements that were discovered here, was made by fusing metal atoms from light transition metals, iron, copper and so on, into lead or bismuth. The first thing you have to do is to decide which metal you want to begin with, because you have to load that into the ion chamber at the start of your accelerator. Some of that is evaporated and it goes into a long tube and it's accelerated up, and it goes up to a speed of nearly 1/10 of the speed of light. If it goes too fast, when you create a new element, it'll fall to bits. If it goes too slow, you'll never make the Sorry. It goes down a long tube, through the wall, into a new chamber. And in the chamber, there's a lead target whizzing round so it doesn't get too hot. Past the target, out of the back of the target, every so often comes just 1 or 2 atoms of the element you want. And they go into a separator. And the separator gets rid of all the other ions and takes the elements you want to the detector. The detector is a lovely shiny piece of silicon in a special detector developed here in Darmstadt. And then you sit in the control room and watch the results.